This is the Financial Thought Exchange podcast, where you learn from the leading thinkers in finance. I am your host, Lotta Moberg, and my guest today is Oswaldo Zapata. This is our third conversation on quantum computing in finance, the exciting and very intriguing topic about where the financial profession might be going in the future. Now, Osvaldo is a co-founder of the Quantum Finance Boardroom, which is an online community advancing the use of quantum computing in finance. He is dedicated to bringing the theory and practice of quantum computing in finance. And he is here as the author of the chapter Quantum Computing in Finance, which is part of our monograph, AI in Asset Management, which is a collaboration between the CFA Institute Research Foundation and the Institute's Research and Policy Center. So thank you so much, Oswaldo, for joining me.
Thank you. Thank you, Lotta.
Now, if you haven't seen our prior conversations on this topic, I highly recommend you first listen to number 1 and 2, parts 1 and 2, and this is part 3 of the conversation, where in the prior parts, we're a little bit more technical, so you'll have a good grounding for what the technical parts that we are talking about. And this conversation will go into more about what the applications might be for in finance in the future of quantum computing. So perhaps, Oswaldo, you can just give us your general thoughts about what are the kind of problems. We talk about problems that quantum computing may be applied to in finance. What are the feature of those problems that we might be looking at?
Yeah, so there are two sort of problems that I see that the industry is trying to focus on. First is optimization problems, because we can use machines that are specially designed to solve optimization problems, even though they are very imperfect. You know that we can have some results like very soon. And then all processes which demand very intensive use of resources, computers. So this is a second option: pricing, of course, and then machine learning processes, Monte Carlo simulations. These are the main subjects studied today. And there is something that I didn't mention in the previous conversations. It's a concept you will always see, which is entanglement. Okay, so I think it's useful to say it. You cannot speak about quantum computing without saying what is entanglement. So let me just say briefly, what is entanglement, which is the key of solving why quantum computers are so powerful. Okay, so this is the example where you can see physically what is entanglement and why this can help solve these difficult problems. Why you can have access to these multiple dimensions, as you mentioned, that classical computers cannot. Okay, suppose you have two qubits, and these are two atoms, let's say rubidium atoms, separated. They have never interacted between them since the origin of the universe. They have been isolated. So you have one here and another one here. These are two single qubits, two states with two states, 0 and 1. Okay, and then you bring them together, they interact, and then you separate them. Now, it doesn't matter how far these two systems are, they behave as a quantum system. Now, these two qubits, physical qubits, in fact, they form one single entity, which is at two qubits. Okay? This is what happens in a quantum computer. You have the quantum computer is here with all these components, and then the qubits enter, for example, state 0. When they enter the system, they get entangled. They interact between them in a way that you want them to interact, of course, by entering these gates. What these gates they do is that they entangle these systems, so they increase the space of solutions that you can then study with this quantum computer, and then when you measure at the end, you get the results. Okay, this is something you also ask in the first conversation. Is everything is probabilistic, right? So the results you will measure here are probabilistic. So this system may run many times in order to find the whole probability distribution, for example, you want, right? And then select the best candidate, for your solution.
So just to clarify what you just said, so we're both in separate rooms dancing discotheque, which is completely random, right? We get together and we start dancing salsa together, right? So now we're synchronized. But then when we forget about that and go into room, we keep dancing salsa, right? As if we're kind of dancing
Yes.
together. But then there will be
Uh,
some errors in the synchronization as well after a while.
Absolutely. Doesn't matter how far apart these two systems are. One can be in this side of the universe, the other one can be in the other side, right? They still have some correlations, and that this complexity helps for problems, for example, like optimization, portfolio optimization, and the covariance matrix, all that. This is something unseen in classical physics, and this is the main property that allows quantum computers to be much faster, okay, than classical computers. There's a lot of discussion, of philosophical discussions about how this happens, if the world is real, Einstein, Bohr, all that. But more or less, this is the idea. The idea is that these two things that are initially uncorrelated, they come close together, maybe because there is a quantum gate, as in a quantum computer. And then when you separate them, they are still entangled. This means they speak to each other, you know, doesn't, regardless of how far they are in space. More or less as the example you said, okay? Come together, you go, but then you keep this experience, something happening there of that previous interaction. And this entanglement is very important. If you want to go a bit deeper, you need to understand entanglement. It's more complex than just a simple concept of qubit, right? But it's a key.
And so, getting back to then, what then are the features of the problems that we'll be looking at in finance, where this entanglement um, becomes useful?
So yeah, as I said, any optimization problem and any problem that is difficult to solve with classical machines, for example, Monte Carlo optimization, simulation, sorry, or machine learning processes, these are candidates for being studied with quantum computers. Now, and that's why in fact, I founded the Quantum Finance Ballroom, is because we have a collection of finance and quantum experts, and it's bringing the two communities together, that we will know the subjects that quantum computers can be helpful, to solve. So it's an institution. For example, let me mention which you have a JP Morgan, for example, who working on that, Wells Fargo. These are huge institutions. They work in they have a research groups in quantum computing for finance, also because they have the resources to access these quantum computers. Okay? It's clear that these quantum computers, the most advanced quantum computers, you can access them in the cloud, and they're not cheap. And then when they will be available, if financial institutions want to buy them, of course they would need to have to allocate them the appropriate space. So this is not something, because people sometimes ask, yeah, will I have a quantum computer at home? No, never. Right? Quantum computers is not for solving problems that a classical computer or your phone can solve. Right? There are some things we still do. I don't know, my fingers, like a 2 plus 3, for example. Still count with your fingers, even if you have your phone. Right? You don't take your phone to do some things. Right? Use maybe your fingers. And then the same with a quantum computer. The quantum computer will solve these very intensive, very complicated problems that classical computers cannot be able to solve. For example, in pharmaceutical, material sciences, and these are problems, pharmaceutical and material sciences, because these are quantum problems, right? So, in order to simulate a quantum problem, the ideal, scenario is to have a quantum computer that can simulate a quantum system, right? Why to use a classical computer to simulate a quantum system? So that's the idea, right? So the first problems will be, of course, in the ones people are developing now, such as portfolio optimization, machine learning. Even though there are, of course, a lot of challenges still, but these are the problems that people are studying, and these big institutions are studying. But it's something, hedge funds, of course, but for finance professionals who are interested in quantum computing, there are many other ways they can capitalize also in this new emerging technology.
So knowing that there are institutions out there that are studying this, at least, what's the probability there are some cool hedge funds out there on the cutting edge that are right now doing the algorithmic trading based on quantum computing?
Yeah, they they're doing it, but only
Mhm.
the research stage. Of course, there is no way they have computers of millions, and
We
this
just know it's not good enough yet. Like, it just would not
no,
be profitable for a company to apply this and beat the market right now. Like, that's not the hidden
absolutely,
secret of the markets right
absolutely.
now. Sh
Not now. So the companies developing quantum computers are the usual suspects, always Google, Amazon, IBM, right? They have the biggest computers. And then on the other side of the world is China. And of course, nobody knows what is happening in China. And when they say something, you may expect that in fact it's just a tenth of what they really have, right? So concerning when will we have the first large scale quantum computers solving problems, real problems, in this side of the world, we think, as I said, 3, 5 years, maybe
Mhm.
7 maximum. However, people speculate that maybe in China, this will be much less, maybe now or in 2, 3 years. And this has to do, of course, with the threat of that quantum computers pose to cybersecurity.
Mm. So, I was also thinking about another application, like when it comes to unstructured data, when you have a lot of unstructured data, like a news flow, we have a lot of talk about things like that with AI now digesting those kind of data, massive amounts of unstructured data. Is that a potential field of application as well for quantum computing?
Yeah, applications in machine learning as a subfield, of artificial intelligence are many. But as I said, the challenges is still, people are still looking in a speculative way what can be done. Right? Don't forget that machine learning is something that was stuck uh, 12 years ago, and only 10 years ago really, start um, getting attention. So quantum experts, they look at machine learning and AI as what can be done there, right? But it's still very incipient.
Gotcha. And then you did mention cybersecurity, which is an
Mm.
interesting field. So you're right in your piece that I, of course, recommend everybody to read. It's full of great information in there and insights and on the cybersecurity front, kind of mentioning that. Well, there are two aspects of this, right? On the one hand, you can use this technologies, the quantum computing, to hack into cryptographic barriers, right? On the other hand, it also opens up opportunities to create new barriers and new cryptographic encoding to mitigate that. So what do you if we have those developments in parallel, what would you foresee is moves the fastest? Are we more or less safe here in the quantum computing world?
If there is one algorithm in quantum computing that you have to remember the name, it's called Shor's algorithm. Shor, okay?
Short, like a
Shor,
short.
yeah, without the T, Shor. Peter Shor is a computer scientist at MIT in the 90s. I remember when he published that paper. I was interested on these sort of things. I was doing my career in theoretical physics. Everybody started talking about quantum computing. So here's the thing. The thing is that you have encryption methods use all over the internet, the data, which is called, one of them is called RSA. Okay, these are the initials of the three people who discovered that, who invented this encryption method, is used all over in the internet, right? So to secure data, transactions, everything. The idea of this algorithm is to these protocols, the appropriate word, is is that you can have some mathematical problems which are so difficult that you can use them in order to secure your data. It's like a padlock, a digital padlock. Okay, you have here all the information, and then you have here a padlock which is digital. Okay, so you in this protocol is relatively simple to explain. It's not exactly like that how it works, but it's more or less. Okay, you have two numbers, you multiply them, and then you ask what are the two numbers that I used in order to find this other number. Okay, these numbers are not normal numbers, are prime numbers. Remember that 3, 5, 7, 11, and so on. Right? So, for example, if I say 15, just like this, you say, okay, that's 3 and 5. It's a joke. So if I use 15 as a padlock to secure my data, anybody can find it. Okay, it's so easy. Now, if I say 3,127, you will say, okay, that's not so easy. I can do it because it's still not so difficult. You can try. And then you send me an email later and you say, okay, I found them. I think it's 53 and 57, something like that, or 57 and 59. Okay. So it's not so difficult. But if you have a big number, 600-digit number, and then you say, what are the two prime numbers that I use in order to get this, right?
Also, it's always two. Also, okay.
Yes, or always two. Okay, I say I had two prime numbers, I multiply them, and I got this number. Please tell me. There is no way. Okay, this will take you millions and millions of years. Not only you, but the faster computer, Google has. So there is no way you can find. So that's why they use these numbers, this protocol, in order to secure data. Okay, they say my padlock is this 600 digits number that is the multiplication of two prime numbers, but you will not be able to find the two prime numbers. Okay, so I can really use them, to send data everywhere. The thing is that, as I told you, quantum computer can solve problems much faster than classical computers. And then in the 90s, 94, 95, Peter Shor discovered this algorithm, Shor's algorithm, where he proved that this is proved. Okay, this is not a speculation, this is true. That if you use a quantum computer, you can solve this problem much faster than a classical computer. And again, much faster means millions of times faster. So instead of 2 million years, you can solve that in a couple of minutes. If you have a faster computer, this may be just done like this, like 15. Okay, for a quantum computer, this problem can be very, very easy. So these are sort of things we are discussing in the previous classes, in the previous discussions. So some problems are difficult for classical computers, but they may be very easy for quantum computers. These are the sort of problems. There are not many, right? So also in finance, we need to discover what are these problems. So people think once you have the problem, the solution is maybe easier because you were thinking already, what can I solve with quantum computers? So you need to identify, this is the key, to identify the problems where you can use quantum computers, right? So the quantum computers can solve this much faster. In this case, break RSA encryption is called. So of course, how many qubits do we need? Okay, how big must be these quantum computers in order to solve these problems? In the West, it's expected that IBM or one of these companies would be able to solve this problem, break RSA, in 7, 8 years. Some people say 10, some people say even 5, 3, but let's say 7, 8 years. Okay, it's a good average. And then this means that in the West, we will have computers that will be able to break RSA in 8 years. But maybe in China, they already have the computers, or they will have it in 3, 5 years. So they could access
And when you
all.
say, just to clarify, when you say in 8 years, we were talking about long time spans of computing here, but you're saying there will be in 8 years a computer that can solve it reasonably fast, not that current computers take 8 years to solve it.
No. Yes, sorry. I mean, in 8 years, we will have the computers. They will solve it in seconds, let's say, or minutes. Let's say hours. It's the same, for practical reasons, it's exactly the same. Hours, a bit bigger, maybe minutes or even seconds. But no, yeah, I meant in 8 years, we will have these computers in the West. But maybe in China, they will have it in 5, 3 years. And it's the same. I'll say I'll take the perspective of the West. Okay, so Chinese, I think they would think the opposite way. So Chinese, they say, okay, no, we say if China can have this quantum computer in 3 years, they will be able to read everything, right? That a bank storage there, right? Or military, also social, security numbers, whatever, everything, all the data can be accessed by those having a quantum computer. And of course, this is in the case of very sensitive data. This is a huge problem, all right? Because suppose someone can access, I don't know, government or military data. This could be really a problem, right?
So how you
So
describe it now is that encryption is ahead of decryption, so to speak, in the sense that this Shor
Yes.
algorithm is very complicated and it exists. Solving it another almost a
Yes.
decade from now.
So in theory, on paper, we know that that this algorithm will break RSA. The thing is that the computers, the real computers, are not yet, there. So, but we will have them in 3, 5, 7 years. Okay. Once we'll have the computers, we'll be able to break, and then we can have access to all data, which is online or safe in banks, whatever, okay, in data centers. So here's the thing: the problem is also that is not when someone will have the quantum computer. The problem is also that they may be um, they call it the, harvest now, decrypt later. Okay? They are maybe harvesting now all the encrypted data in order to be decrypted in 5, 7 years when they will have the computers. Okay? So you can have the 600 digit numbers, you keep them here, and then you say, okay, when I will have the computers, I will read what is inside, right? Why? Because passwords and many things do not change. The structure of these cybersecurity systems is not something that is being renewed every year, every 6 months. No, it takes a lot of time, right, and a lot of resources, financial also resources. So this may take 10, 15 years to change from the encryption standards we use today to the new ones, right? So NIST, which is the National Institute of Standards and Technology in US, they have already um, approved a set of protocols which are safe regarding the new generation, the first generation of quantum computers. This doesn't mean that there will be a new generation of quantum computers that could break that. So banks, they are focusing more on this than on developing uh, quantum computers for applications, because they know that this is a real threat, right? So if you see how they balance um quantum computation and quantum security, they focus a lot and more in quantum security. They think is a is a bigger problem. Now the benefits and the risk. They think the risk of quantum computers is maybe bigger than the benefits that quantum computers can give.
So when you walk into your financial institution 10 years from now, let's say when we have this applied in our institutions, what would you think that, if anything, will be different in the workplace here? Will there be armies of quantum computer typists here or like programmers sitting here at the desks? Or will this be just a piece of software that you plug in, you won't notice anything or anything in between?
Yeah, when I finished my PhD, I don't know if I told you that, but many of my friends, they moved to finance, okay? Because we have the skills, we know the computer science. So most of them, they moved to finance. So they became quants, right? I think that if you are in the very technical side, uh, working for a financial institution, I think you maybe see in the future a lot of quants which have quantum expertise. I call them quantum quants. So quants that know how quantum computers work and how to program these quantum computers. This will be in 10, 15 years, you will see more and more of these sort of people. It's something that today you don't see because we are still, in the early stages. And then we have not many, honestly, not many. If you, for example, you check JP Morgan, you see the job offers, they ask for people who have the quantum background in order to work in these quantum computing for finance programs they have. They ask you no financial background at all, zero, right? So more or less happened the same when I was 20 years ago when I finished my PhD. The same happened. They don't require any background in finance just to have the technical skills. And this will be, I think, the norm in 10, 15 years. Many people, if you are a technical person, will be working in quantum programming for quantum computers, right?
Oh,
You will
that's
not.
interesting you say that. So most people who are technical will be in the quantum field. Because I was kind of wondering why when we think about like computer literacy today, there we have a certain sense of what that means. Now you also need to understand AI, right, to be in that
Yeah.
group. And you're saying it's actually going to be quantum computing more than probably
Yeah.
most skills here that is important.
Yeah, I think you will not be programming classical computers to solve problems that quantum computers are much faster, right? So there is no need for many people working on classical computers, right? When you know that the quantum computer of your competitor they are doing things much faster. And as I said, much faster means that it's not months, it's maybe minutes,
Mm.
right? So of course you will have more people working. Now the quantum ecosystem is very wide. You don't need to be a technical person, but you can, for example, be interested in quantum investments, right? Or invested in quantum. This is also something we focus in our community is people who are not technical, but they want to know where to invest in quantum, right? So as I said at the beginning, you have not only quantum computation, but you have also quantum sensing, you have quantum cryptography, quantum communication. So these these three types of technologies have their own time horizons, risk. So this can be evaluated, and people in finance are looking at this closer to invest and diversify the portfolio, technical portfolio. So this is something also that I will see more and more in the future. People investing in quantum and following
Just like
closely what is happening.
So just like now where we're with AI, right? You can be ignorant, you can be an engineer, and you can be like vibe coding in AI in the future. You can also be like vibe quanting in this field.
Because the conversation we have now is we are having a very early adopters conversation, right? But the same, in quantum in AI was 10 years ago, 12 years ago. These were like the same small conversation between small group of people, but now everybody's talking about it. And now the next technology could be quantum computing. Now we are still a small group of people interested in that, but I think you will see more and more people, even declarations by the CEOs of these big companies, for example, Nvidia, Microsoft, IBM, talking more and more about quantum as the next disruptor,
Oh,
in
that's
this
fascinating. I
space.
really hope our listeners have gotten a sense of how the future in their field might change, all for the better. And it's really exciting field. And thank you so much. Thank you so much for being with
Yeah,
us and
thank you.
sharing your
Thank you,
knowledge.
Lotta, for the invitation.
And thank you, everyone, for tuning into the Financial Exchange Podcast. I've been your host, Lotta Moberg. My guest has been Oswaldo Zapata. This was the third out of 3 conversations. So if you missed the prior 2, make sure to check out those 2. We cover a lot about quantum finance. I learned a lot. I know you will as well. Now, Oswaldo Zapata is not only the co-founder of the Quantum Finance Boardroom, but he's also the author of a quantum computing piece that is part of our recent monograph in AI finance. So thank you so much for the contribution there. And thank you everyone for listening. And we will see you again soon.
For more information, please visit rpc.cfainstitute.org/research-foundation.